So then next one is the convert name to structure. Tetraamine. Tetraamine means CaNH3 taken 3 times. Aqua, water. Chloro, Cl. Cobalt, CO. Chloride, Cl. Right? You have to write it in the complex. Right? There is no positive charges, right? So you have to write complex CO, cobalt, amine, aqua, tetraamine, CH3 taken times water, aqua, chloro, Cl, right? So dichloro, it is only single chloro. If you write only one chloro, what is the oxidation state of cobalt? NH3 is the neutral ligand, water is the neutral ligand, Cl is the minus negative charge, this Cl also minus negative charge, minus 1, minus 1, that becomes minus 2, cobalt becomes plus 2. That's why you have to write it as a Cl2. Then only this becomes minus 1, this becomes minus 2, this becomes minus 2, that's why cobalt becomes plus 3. Right, once again, triamine, aqua, chloro, cobalt, 3 chloride. Why it is not cobaltate? Because this complex is a positive charge, just like NaCl. This one is Na, this one is Cl. So this one is a positive charge, that's why cobalt. How it becomes 3? That Cl, inside Cl is the minus 1 charge, the outside Cl2 is the minus 2 charge, cobalt becomes 3. After this complex there is a chloride, that's why you are writing as a Cl2. Right. Potassium tetrahydroxozincate, potassium, so there is a K, tetrahydroxo, OH taken 4 times, zincate, zinc 2. Right. So you have to write by adding these potassium K, right? It is a positive charge, zinc, Zn, metal atom followed by ligand. How many hydroxo? 4 hydroxo, right? So zincate 2, this complex is negative, potassium is positive, that's why it is a zincate, it is a 2. OH becomes, it is a 4 negative. So if you want to get 2 oxidation state of zinc, how many potassium should be there? K2. Then only the zinc becomes plus 2. Then only the zinc becomes plus 2. Otherwise the zinc becomes does not matches. K2 Zn OH taken 4 times. Right? So what is the answer for that one? I am writing clearly here. K2 Zn OH taken 4 times. So for this one, CO NH3 taken 3, water, chlorine, chloro, Cl2. That is the answer. Right? Answer. Potassium trioxalato eliminate. Potassium K, trioxalato C2O4 taken thrice, oxalato, eliminate Al. Right. So potassium K, by adding all these 3 you can write it. Right. So potassium K, what is the answer? Right. Potassium complex Al, C2O4. What is the charge on the oxalate? Trioxalate. They have given trioxalato. So C2O4, that becomes minus 2, minus 6. Aluminum, it is eliminate because this one is a positive charge, this one is a negative charge. So eliminate 3. When it becomes 3, if it is K3, this becomes minus 6, this becomes plus 3. That's why aluminum becomes plus 3. You need to practice, otherwise this will be a lot of confusion. Then only you will understand. You need to practice oxidation numbers. You need to understand the nomenclature rules. Right. So dichloro bis ethylene diamine. dichloro Cl2, bis-ethylene diamine En taken twice, right, cobalt CO, right, cobalt 3. So what is the answer for this one? What is the answer for this one? Cobalt neutral, right? It is a neutral. Ethylene diamine, right? Cl2 dichloro cobalt 3, cobalt 3. So cobalt 3, when it becomes cobalt 3, so this is minus 2. What you have to do? There is a, right, you have to write the plus 1 charge, then only the cobalt becomes plus 3, right? So minus 2, what is the oxidation state? How do you calculate? I told you in the beginning. How do you calculate? So x minus 2, that is equal to plus 1. So x is equal to plus 3. You have to write plus 1, right? Because it is dichloro bis-ethylene diamine, dichloro bis-ethylene diamine cobalt 3, cobalt 3. When it becomes, if the complex is positive, you have to write it as a cobalt. I told you, if the complex is positive or neutral, you have to write cobalt, metal atom only. If it is in this last class, platinum case, we have taken platinum is a, right? So this complex is positive, that's why you are writing as a cobalt 0. Right. Tetracarbonyl nickel 0, right? Tetracarbonyl CO taken 4 times, nickel 0. So nickel tetracarbonyl, it is a neutral ligand. This nickel 0, nickel, the oxidation state becomes 0. The complex also, there is no charge. It is a neutral complex, tetracarbonyl nickel 0. That is the answer. So, right? If you have any doubts, you can ask. There is no problem, right? So you need to practice what are the ligands, what are the charges on that one. Practice the nomenclature rules. Practice the, right? So they have given textbook. They have given some exercise 7.11 and 7.12 are homework. 7.11, 7.12, Telugu Academy, page number 260. Page number 260 is the homework. 7.11 and 7.12 are the questions are homework. Just practice. If you have any confusion, just let me know. I will explain once again those 7.11 and 7.12. So far we discussed the nomenclature of coordination compounds. The next one is theories. The first one is Werner's theory of coordination compounds. So Werner won the Nobel Prize in the 1913 year. He worked extensively on the coordination chemistry. So Werner was first to formulate his ideas about structures of coordination compounds. So who is the fundamental of this coordination chemistry? Werner is the fundamental chemist, Swiss chemist of this coordination chemistry. Werner is the first first he proposed this coordination chemistry and he worked extensively on the coordination chemistry. That's why he won the Nobel Prize. So what theory says? What is the main concept? This theory explains the arrangement of ligands around the central metal. How the ligands are arranged around the central metal atom. He proposed that every central metal atom, every central D black element, every central metal atom shows two types of valencies, that is primary valency and secondary valency. The complex compound metal ion shows two types of valencies, that is primary and secondary valency. Generally, primary valency is satisfied by negative ligand, whereas secondary valency is satisfied by the negative as well as neutral ions. What he is saying, what he said, what he said, what he was said, what he was said. The primary valency was satisfied by negative ion, whereas secondary, you will come understand very slowly what is the primary, what is the secondary valency. Satisfied by negative ion, the secondary valency is satisfied by negative as well as neutral ligands. So he proposed that every metal is having the fixed number of secondary valency. That means every metal is having the secondary valency is fixed. That means, so the secondary valency called as coordination number. The secondary valency tells about the, according to him, the secondary valency tells about the coordination number. He proposed that every metal is having a fixed number of secondary valency. That means, suppose if it is generally 4 and 6, he proposed 4 and 6 coordination numbers. He predicted that the structure of different complexes with coordination number 4 and coordination number 6. In this one, cobalt is showing the coordinate. This metal is having the fixed coordination number cobalt. He observed all the cobalt complexes. In that one, cobalt is showing +6 oxidation state. According to him, every metal is having the fixed number of secondary valency. That is, he is calling as coordination number. So cobalt is having the second. What is the secondary valency of cobalt? According to him, the coordination number of cobalt is 6, right? So that 6 is calling as secondary valency. So coordination number 4. If you see nickel is showing tetrahedron. It is showing the 4 coordination number. Platinum is also showing the 4 coordination number, but the structure is square planar structure. So what he is telling, he proposed 2 valencies. One is primary, secondary valency. According to him, every metal is having the fixed secondary valency. That secondary valency is calling as coordination number. Based on that coordination number, he proposed coordination number 4 and coordination number 6. Coordination number 4 is having the 2 types of geometries. One is tetrahedron geometry, the next one is square planar geometry. Coordination number 6 is having the octahedral geometry. So what Werner did is, he mixed with cobalt trichloride and ammonia. Cobalt trichloride and ammonia, he mixed both two. That forms different, when he mixed both two components, that forms different coordination compounds, different. So he observed that these type of coordination compounds are formed. So how he observed? Based on their colors, this color is different, this color is different, this color is different, this color is different. So in the first one, if you see cobalt bonded with 6 ammonia, the outside is 3 chloride ions. In the second one, cobalt is bonded with 5 ammonia, 1 ammonia is going outside, one ammonia is left over. That's why the color is different. So the one chloro is inside the complex. In the fourth one, so slowly the ammonias are decreasing. 654. So if the ammonias are decreasing, slowly the chloride ions are going inside the coordination sphere. What is the meaning of this one? On the base of this one, cobalt always showing how many ligands around the cobalt? 6 ligands. Here is 5 plus 1, 6 ligands. 4 plus 2, 6 ligands. 4 plus 2, 6 ligands. So according to him, every metal is having the fixed number of ligands. Those ligands generally is calling as coordination number. So if it is decrease, if NH3 5, the Cl is going inside. If NH3 is 4, 2 Cl are going. If NH3 is 4, 2 Cl. So these two are same formula, but they are showing different colors. That what is the difference in their geometry? Cis and trans geometry. There is a difference in cis and trans geometry. So the last one, all NS3s, three NS3s and three chlorines are inside. He observed different, by mixing the cobalt trichloride ammonia, he observed different complexes and their different colors. Why these complexes are showing different colors? Based on the ionization. So these complex structures are different, that's why they are showing the different colors. So in the ionization in water, only the outside is ionizable sphere, ionization sphere, the inside one is non-ionizable sphere. So this one is not ionized, sorry, NH3 taken 6 times. The outside 3 Cl3s are converted into 3 Cl minus, because this is ionizable sphere. In this one, 2 Cl are ionizable. The coordination sphere is not ionizable. In this one chloride is ionizable. In this one chloride ionizable. This is not ionizable. In this one, there is no chloride ions. That's why no ionization takes place. So the total number of ions, this one is 1 ion, this one is 3 ions, total number of ions are 4. In this one is 1, this one is 2 chloride ions, that's why it is 3 ions. In this one, this is in the water. If you I told you in the beginning, the outside coordination sphere is, you can call it as ionizable sphere. How many number of Cls? That is 3 Cl minus is available in the ionization sphere. In this one, 2 Cl minus, in this one, 1 Cl minus, in this one, 1. So this is how many ions? 1 plus 3, 4 ions present in the water. 1 plus 2, 3 ions present in the water. 1 plus 1, 2 ions present in the water. 1 plus 1, 2 ions are present in the water. So what he did is, he added one, in the first one, he added AgCl. Calculate added AgCl. So how many moles of AgCl is added? Silver nitrate. Sorry, he is added, I think, silver nitrate. Silver nitrate he added. So it forms the, silver is combining with the 3 chlorine. 3, so he added silver nitrate. So once he added silver nitrate, that is combining with 3 Cl minus. So 3 moles of Cl minus. How many moles of AgCl he observed? 3 moles of AgCl is observed. So what he did is, he has taken the bowl, he added first complex, first he added 1 mole of AgNO3, 1 mole of AgCl is formed, then 1 mole, then 1 mole. How many moles he added? 3 moles AgCl is neutralized with, if he is added 4th mole, it does not react. What is the meaning of this one? 3 Cls are outside the complex. 3 Cls are outside the complex. That's why 3 moles of AgCl is formed. In the second one, 2 moles of AgCl is formed, because how many chlorides? This one does not react with AgNO3. How many chlorides are outside? 2 chlorides are outside. That's why 2 chlorides can react with AgNO3. It forms the 2 mole. It forms the 2 moles of AgCl. In this one, 1 mole is outside. That's why 1 mole of AgCl is formed. In this one, 1 mole of AgCl is outside. So why he did this type of addition of AgNO3? Because he wants to know the how many chlorides are outside the ionizable sphere, how many chlorides are outside in the ionizable sphere. To know that one, he added AgNO3, calculated amount of AgNO3 based on formation of AgCl. He observed that how many chlorides are outside the coordination sphere. Based on that one, he proposed these coordination complex, how the structures are, how the ligands are related to, how the ligands are attached to the central metal atom, how many ligands are outside the coordination sphere. Right? Hope you understood. Once again, in brief, cobalt trichloride, when combining with ammonia, it forms different complexes. when these different complexes generally showing the different colors. So yeah, he thought that why these complexes are showing different colors, because the structures are different. Then what he did is he every complex, yellow color complex, he put it in the water. So when we put it in this complex, that is ionized in the water. Once it ionizes the water, it gives the 3Cl ions and then the complex ion. So what he observed, 4 ions are formed in the water. For that one, what is added? Silver nitrate is added. Once he added silver nitrate, the 3 moles of AgCl is formed. What on the basis of this result, what he observed, on the basis of this result, what he observed, 3 moles of AgCl formation indicates 3 chloride ions are outside the coordination sphere. These 3 chlorides are present in the ionizable sphere. That's why there is a formation of 3 moles of AgCl is possible. Then only, if the 2Cls are outside the coordination sphere, that is in the present in the ionizable sphere, it forms the only 2 moles of AgCl. So these moles of AgCl indicates how many chlorides are outside the coordination sphere. Based on that one, he proposed the different structures. So, according what Werner proposed, two types of valencies. Primary valencies, he proposed that primary valency is ionizable, secondary valency is non-ionizable. So, what are the defects in the Werner's theory? So why certain elements is forming these coordination compounds at the 1900 time, right? There is no instrument, there is no sophisticated equipment, there is no such chemicals, even though he performed a lot of research. But at that time, he couldn't explain why only some elements are showing this remarkable property of forming the complex compounds. He was unable to explain that why certain elements only forming the complex compounds, why sodium, why the other elements other than D black elements, very rare, those does not forming, why those elements do not forming the coordination compounds. He was unable to explain the magnetic and color properties, and also he was unable to explain the stability of complexes. There are some defects of Werner's theory, right? So what we discussed today, Werner's theory, he won the Nobel Prize. He proposed two valencies, primary and secondary, right? Secondary valency, generally every metal is having the fixed ligand atoms, that is he is calling as that coordination number. So he did one research on the cobalt by mixing the cobalt trichloride and ammonia. He got different complexes with different colors. So to know the structures of those complexes, he did experiment with silver nitrate. So when he did experiment with silver nitrate, there is a formation of a white PPT of silver chloride is formed. So how many moles of silver chloride is forming? Based on that one, he proposed how many chlorides are outside the coordination sphere. Based on that one, he proposed the cobalt containing complexes structures. Right? Thank you. We'll continue in the next class.